Great. Hello. I'm going to talk about, I think maybe we should call it runtime transparency. I'm not sure. Yeah, all right, let's go. My name is Fredrik Strömberg. I'm involved in these companies and projects. And one of the projects I'm involved in is system transparency, which I made up because I wanted to prove to an extent what we're running on our servers. It turns out you can't prove it, but you can, give claims about it. I call it system transparency. Hal Finney called it transparent server back in 2001. Keylime is sort of similar to it. Project Oak is also sort of similar to it. Apple Private Cloud Compute, which was launched earlier this year, in their excellent blog post, which I think you should all read, or I can highly recommend it at least. They talk about verifiable transparency and runtime transparency. And given that system transparency has been a project for 6 years now, and it's tied to how we want to implement it, I thought perhaps there should be a vendor-neutral term which should not be system transparency, or Apple Private Cloud Compute for that matter. And I propose perhaps runtime transparency. So what is, I'm going to talk about how I think about this concept and in what ways it's general. So the way I think about it is we have transparent systems, or we want transparent systems, and the fundamentals are hardware, software, identity, and behavior. More fundamentally, it begs the question, what must I trust? Or rather, what must I be vulnerable to? Because trust is about vulnerability. And I think we need to be, we pretty much have to be vulnerable to the hardware and the operator who provisioned it. I know maybe you don't need to in some cases, but bear with me. So you have the hardware and the individual who touched the hardware. You have the software and the individual or individuals who touched the source code. That's what we have to be vulnerable to. Which begs the question, how do we construct an authentication mechanism for these things we must be vulnerable to? Clearly, there should be at least 4 keys here, right? One for the hardware, one identity for the hardware, one for the software, one for the operator, one for the developer. And we want to tie these 4 things to the behavior of the running system. And that's what this system transparency authentication mechanism will try to provide. It will try to provide accountability for running systems. And if we think about authentication mechanisms more generally, what is it? Well, we have some type of authentication that is done by establishing trust in a certificate. The certificate contains an identity and a public key, and the authenticated key is used to establish secure communication using ECDH or something like that. And that's TLS. So we have identity, like domain name, human readable identity. Then we have cryptographic identity, the public key. But if we look at remote attestation authentication mechanisms, they tie human readable identity, cryptographic identity, and other claims about the remote system to a public key that we then use to establish secure communication. So we authenticate this public key or this ECDH handshake. And we can use this authentication both to authenticate a secure communication connection with WireGuard or TLS or whatever, or we can use this to authenticate the public key that we use to sign things, like files. So let's go back to the fundamentals. Computers have a physical reality, and that reality is hardware. If we zoom in on that. Actually, I'm not going to do that. I don't have time to talk about hardware. Okay. So we can model this. We can model hardware plus software leads to behavior as a 2x4 matrix where we have a few phases. And we think about them implicitly, but I've tried to make them explicit. So we have the human readable phase of the software, which is the source code. We have the in-brain process of your conceptual understanding of the source code, including your mistaken assumptions about the behavior of the the program, because whoever wrote it was writing spaghetti code. And then we have the hardware. The human readable version of the hardware is the blueprint or the Verilog. And then we compile the source code, or we synthesize the Verilog into a physical construction, or a PCB in the case of hardware, or a build artifact in the case of software. But what we do, where we place our trust, is actually in the the running system's reachable state space. So if you have a piece of hardware that only needs to do one small set of behaviors, you could implement it all in Verilog. That's great. But if you don't have the money to make your own chips, one for MS Word, another for Apache Web Server, a third one for your WireGuard VPN relay, and so on and so forth, you need programmable hardware, which means that you have on a 32-bit system with 1 gig of RAM, you have more possible states than there are elementary particles in the universe. Thus, the purpose of software is to converge the running system's reachable state space on the small set of behaviors that you care about, and not the ones that the attacker cares about. And we do this by connecting these phases using various technologies, which I don't have time to talk about in detail, but essentially what we need is to use secure network communication protocols and their authentication mechanisms. We take inspiration from those. We combine that with remote attestation and reproducible builds and transparency logging with distributed trust assumptions, and boom, we have remote transparent systems. There's also some underlying philosophy, which I don't have much time to go into, but essentially my point is that there are two complexities that matter here. The first one is amazing. The only quantifiable security margin technology we have is cryptography, because we can formulate it in terms of how many exajoules of energy, how many Dyson spheres, how many tons of computronium, and how many millennia do I need to crack one instance of AES. And then there's the conceptual complexity, which will continue to rise. And as complexity continues to rise, the expected behavior of the system and the actual unintended and surprising behavior of the system will diverge. The delta between them is attack surface, and our job is to figure out how do we keep them together. And my short list is this, which I'm happy to talk more about some other time because I'm out of time. Thank you so much.